Hi everyone. So let's begin. So I believe this week is about programmable data planes. So while we have touched upon the topic of programmable data planes in the previous classes, probably now would be a good time for us to formally get introduced to what programmable data planes are, right? So we've learned something about the paradigm of SDN, right? Software defined networking. And all of this was, I think, probably covered in the previous classes. I'm talking about the main videos, that is. So that's where you get elaborate explanations of all these things. So you have software-defined networking, and one of the main abstractions that software-defined networking put forward was the fact that there is this control plane and there is a data plane, right? The control plane houses a lot of things. We previously looked at a lot of aspects of the control plane, like network function virtualization and all of that. But in bare bones, for this to understand programmable data planes, let's assume that the control plane is basically a set of operating systems, network operating systems. Right? And this network operating system gives instructions to the switch that is kept in the data plane, right? So for now, let's consider this simple model. It's not exactly as simple as this, but it's like so you tend to give instructions to the switch, which handles the packets that come in the ingress and then puts the packets out of the right ingress and egress. So input port and the output port. So if you look at this, there are multiple questions that come up. One of the first questions is, what does this communication look like? What kind of messages are being sent? Can you send any kind of messages, or is there a particular protocol? So one of the protocols that we learned in the previous classes was something called OpenFlow, right? So OpenFlow had a particular set of messages, and what did these messages do? These messages influenced a forwarding table. Right? So these messages modified a table which contained entries. So what do these tables contain? It contains entries. Right. So the whole paradigm of controlling the data plane, right, by the control plane happens through tables. So this is the first point that you'll have to keep in mind if you are to understand this. So it's not as it is flexible, but it's not as flexible as your computer, where you can create your own kind of data structures, where you can create your tree, your hash maps, and whatever it is, right? So here it is simple tables, and these network operating systems, just by influencing the tables, the control plane, that is, just by influencing the forwarding tables, they can change the behavior of this data plane. So again, this time I'm taking it slightly from the scratch. So if you have any fundamental questions, or if you have any basic questions altogether, if you want me to explain something that is not being explained here, or if you want me to reiterate something here, or if you want to ask some very, very basic question also, it's fine. this is the place where you can ask such questions and get yourselves updated. Right. So just putting it out there. If you have any questions, feel free to unmute the mic and ask. Don't worry about how silly the question might be, right? Because this is a slightly advanced topic, which it might take some time for you to wrap your heads around this, because it's like you're being it's a fast track course into advanced aspects of computer networks. So it's okay for you to have questions, and you can definitely ask at any point of time, right? Okay, so we have forwarding tables, and the first point that you have to understand is tables are key. In a sense, they are the key, let's say, abstractions, not data structures. They are the key abstractions which help in the network which help in the paradigm of programmable data planes, right? Okay, so now with this context in mind, uh, let us move on to something. Okay, so now now you have a question basically. So I mean, now we can ask a question. So now that we have influenced, or rather we have sent instructions from the control plane to the data plane, right? um is there any other way where we can make this paradigm even more flexible? How do you add more flexibility to this paradigm? How? So the next rather the next evolution, right, the next step evolution was we write custom code and push it on to the switch. Is also called programmable data plane. Meaning the very same way that you write a program for your Java or C or any of those things, right? You write a program and then you compile it. And what happens after you compile it? You get a binary and then you execute that binary. So you do the same thing here, and then you take that executable and you put it onto the switch. So this particular switch, or the programmable data plane, is the behavior of this programmable data plane is not just influenced by the table entries. You are also putting your own custom code, your custom program onto it. So now it becomes a combination of your custom code plus table entries, right? So this custom code and table entries, this combination is a powerful combination. So you change the table entries and then you write custom code that behaves, that kind of modifies and behaves according to how the table entries are, rather, that behaves as per the table entries that are expected, right? So I think right at this point you might not be able to understand this if you have not done any P4 coding, but this is essentially that what you have to know. Custom code plus table entry. So this is the key, right? So I think this is the context that's required for you to understand programmable data planes. So with this, if you see the videos that have been put in this past week, you'll probably be able to figure out um, you will be able to understand this with a better context. All right. So with that in the back burner, probably we can go to answering some questions. Now, again, if you have any questions regarding this week's videos, feel free to ask. All right. So now, which of the following statements about programmable networks is/are not correct? A network that is pre-configured and cannot be changed, right? So this is they say the network is pre-configured and it cannot be changed. Okay, and we're talking about programmable networks. Programmable networks enable network administrators to program the behavior of a network devices using the software. Okay, so this looks true, right? Because programmable networks, they basically enable programmability, right? So programmable networks, they indeed empower administrators to use software for programming device behavior. Yeah. So C, a network that can be controlled and managed through software. This is basically a fundamental characteristic of programmable networks. So this is also true. Programmable networks can only be managed and controlled by a single centralized software controller. So basically, while centralized controllers are common, modern programmable networks, they can use distributed control architectures. So they are not limited to a single centralized software controller. So this is false, right? So I'll explain what the last statement means. So again, and now coming back to statement A, a network that is pre-configured and cannot be changed. So it's supposed to be changed. That's why it's called programmable. So this is false. So the first three are no-brainers, like false, true, true. The last false. So basically what they're saying is you have this particular switch and then you have, let's say, multiple controllers, right? You can either have a single controller or you can even have multiple controllers coordinating to make changes. So that's completely fine. Like it depends on the way you want to manage, right? So or rather, you can have multiple switches, and this switch is having a separate control plane. This has a separate control plane. It's possible. It does not necessarily have to be a centralized controller that controls everything. So that's why D is also false. So the answers are A and D. Right. So here they're talking about something called P4. So the videos would have introduced to what P4 is. So what P4 is basically this custom code that I was talking about. So this custom code is written in a language called P4. So P4 is something that looks a bit like C. It has the C syntax almost. Right? This has the C syntax. So what is the primary purpose of the P4 network programming language? So why did this programming language come up? So is it to program the control plane of network devices? No. So it is basically to program the data plane. It's supposed to be data plane, not control plane. So this is false. The second question, the second option, to program the data plane of network devices. Oh yes, so yeah, this is true. To automate network management tasks. So automation is possible through P4. Basically, you can write programs to automate certain behaviors of the network because that's the whole point of a programmable network. But P4's main role is not in automating management. In the sense, P4, the question is talking about which is the primary purpose. Primary purpose of P4 is basically to program a data plane. So this is basically an effect of programmability. So for the context of this, for such questions, consider this as false. In the sense, you don't have to go for secondary aspects, just go for primary when they're asking for primary. right? So, and then program for writing device drivers. No, device drivers are completely different. So it's device drivers are very low level programming, right? So P4 is basically a high level packet processor. So this is also false. So the answer is just B. Again, if you don't understand something that I'm saying, you feel free to ask, because this is not a very intuitive topic, right? Okay. So we spoke about OpenFlow here, right? So here we spoke about OpenFlow. What is OpenFlow? It's a protocol that is used to communicate between the control plane and the data plane, right? So OpenFlow has multiple versions. So in OpenFlow one, in the initial versions of OpenFlow, you only could compare or match a particular set of fields, and then in further versions of OpenFlow, this increased and this increased and this increased, and then in OpenFlow 1.3, every new version, what is the uh, total number of header fields that can be matched? So fields are nothing but header fields. So what are header fields? Header fields are those packet headers, like for example, IPv4 address, or port number, or source port number, destination port number, even a TCP header, IP header, all of these headers, right? So because packets come, and then we match these headers onto onto what is there in the table, and based on that, we make some decisions. So what OpenFlow did, it defined that you could only match based on some 40 fields or 30 fields. Oh, okay. So I think the answer is right here. Make a mistake. So the answer is 30. Okay. So we have 40 fields. So OpenFlow 1.3, it it supported 40 fields. For example, source port, destination port, source IP, PIP, like that, 40 fields. So you can only match based on these 40 fields. You cannot match based on any other field. So that's one of the limitations of OpenFlow, where it actually defined that only you can match based on these fields. Suppose if I come up with a new algorithm and if I create a new header field, OpenFlow cannot help you there. So this was one of the limitations of OpenFlow, which was overcome by programmable data planes. We'll see what happened, how it overcame the limitation. So which of the following is not a P4 primitive action, right? Which of the following is not a P4 primitive action? Primitive action is like a fundamental atomic action that uh, uh, that uh, this network paradigm kind of gives you. A primitive is basically an abstraction, right? So what actions? Basically, you drop packets, you modify packet, you can forward the packet, you can move the header, or you can buffer the packet. You have so many of these kind of options. So out of all of these options, what is not a primitive action is forward. So this is the answer. Answer is C. So look at the explanation here. So although forwarding is actually a key network function, in P4 it is not treated as a primitive, but it is rather as a result of applying a sequence of primitive actions, right? So I'll explain that. So you get a packet, and then you have a switch, right? And then the switch can apply primitive actions on the packet, right? So what would these primitive actions be? So the packet comes, and then it checks the header, or rather it compares the header with the table, and then the packet is forwarded to the next pipeline stage, and finally you modify the header. See, modify header is one of these things, right? So you modify the header, like add like decrement the TTL value, you modify the header, and then finally you place it on the wire, and then the packet just goes. And that forwarding, right? This final forwarding is basically a consequence of applying all of these primitive actions. So this is a primitive, this is a primitive, this is a primitive, but this is not a primitive. So forward is not a primitive. So this is basically the way P4 is being built. You just have to read the specifications of it, or just watch the video where you'll understand that some of these actions are not primitives and some of these are primitives. Right? So just keep this in your mind. That's pretty much what it is. So primitive is like a basic action. It's like a basic library call that you can do in P4. So I hope that makes sense. It's like let's say in C or C++, you use the plus operator, right, or minus. So these are all fundamental operations, plus, minus. But you can also write your own operation and overload it. So that is not a fundamental operation in C or C++, right? Operator overloading. So it's something similar to that, right? But yeah, so these primitives are like this. And this overloaded operation is like this, right? Where you use these fundamental operations and then you finally find an overloaded operation. So that could be a decent parallel for you to compare with. So now we come towards something called P4 runtime. I do not know how much I do not know how much I can introduce you to P4 runtime. So essentially, it is basically a way in which you can, it's basically an interface which you can use to influence P4 programmable network devices. So it's like this. You have a controller. And whenever I write something on top of the line, it's the control plane, right? I don't have to write that anymore. This is the switch, right? So the controller and the switch are always connected. And what is the name of the interface that allows you to connect it? This is called P4 runtime. It's called P4 runtime, right? So P4 runtime is the interface that helps you communicate between here and there. But this P4 runtime, they're asking which of the following statements are not correct about P4 runtime, right? So with this context, let's look at the options. The P4 runtime provides a standard interface for controlling and managing P4 programmable network devices. So this is true, right? This is basically what I explained. So P4 runtime provides a standard interface to push new P4 programs without recompiling the software stack of target switches. So this is also true. Now, what this means is, see, you have the switch. Right? The switch is like a empty box. It's called a white box switch. Now, what you're doing is you are writing your own code, right? And compiling it, and you're pushing it onto the switch. Right? So now, when you push it onto the switch, so switch is a very it's a hardware device, right? So it's a highly closed hardware device. So usually, when you change the behavior of such baked in ASICs, right? Application specific integrated circuits, ASICs. What you have to do is you have to reload the whole firmware. You have to like reflash the whole thing and then only change it, and then only we can change the behavior of it. So what P4 runtime did was you don't have to restart the switch. You don't have to reflash the firmware. You don't have to do any of those. You just get the binary and then you push it onto the switch. That's it. You just push it on. So that's what it means by recompiling the software stack of the target switches. So basically, it gives you a layer where you can push your binaries onto it without having to disturb the whole software stack or restarting the switch. Right. So this is basically what it means. And P4 runtime, it gives interfaces to do that. Right. So all of this might be difficult to understand without having some practical experience with P4. So take it, assume certain aspects of it, and if you have any questions, you can ask me, right? So this is about B, and then C. Protocol buffers version. Protobuf 2 is used to define the P4 runtime interface. So no, apparently this is not the case. It is defined using protobuf 3. Right? So this is false. It's not 2, it is 3. That's the difference here. That's all. So what is protobuf? Probably might be too much for the class, so you can read about it if you want, right, on the side. P4 runtime API can be used equally well by a remote or a local control plane. Okay, so yes, it is also true. So what is this remote and local control plane? What I'm talking about here is a remote control plane, meaning the control plane is far away from the switch. But every switch itself also has a control plane. It's called a local control plane. You can run P4 using the local control plane as well. So this is something that I did not want to bring in to confuse you, but control plane need not only be remote, it can also be a part of a local environment, right? Local switch. So every switch has a control plane. In the sense, the control plane is where this software runs, and the data plane is where the packets are forwarded or all these hardware-based actions are taken. So anything that you use to control the behavior of the forwarding is called the control plane, essentially. So that could be on the switch or it could be remote as well. So, but P4 or rather P4 runtime can be used by either a remote or a local control plane. That's pretty much what it says. So it's true, true, true. The answer is C. That is what is not correct. Okay. Which of the following statements are correct about P4 language? Okay, so which of the following statements are correct about the P4 language? P4 is a domain-specific language for programming network devices. Yes, it is a domain-specific language for programming network devices. Which domain is it? The domain is networks. That's what. So this is true. So first one is correct. P4 is primarily used for programming the control plane of network devices. Is that the case? No, because you push the binary onto the switch in the data plane. So it is actually used for data plane, not for control plane. So the second one is false. P4 is case insensitive language. So this is going to the specifics of P4. So P4 is kind of like built on top of the C syntax. So it is case sensitive. The C is also case sensitive, right? So this is also false. And D is P4 is statically typed language. This means that types are checked at the compile time, right? Which leads to a more deterministic behavior. So, which means you cannot, you don't have even the switch won't throw errors during runtime because it's like once you bake in the the program, it has to run. So, which means before you put the binary on, you need to make sure that there are no syntactical mistakes, or rather such kind of type check based mistakes. So it's prudent that this is all checked. So this is actually correct. So it does not, it won't even let you compile if there's a type mismatch. Okay. And again, P4 is protocol dependent language. So the one of the key design goals of P4 was protocol independence. This is what allowed it to adapt new protocols without rewriting the language itself. So, which is where this is false. So, which of the following are correct? A and D. Okay, 6. And then now 7. How many bits are used to identify the service path ID field in network service header structure? So network service header structure is something that is used for network management, and the path ID field in network service header uses 24 bits. This field is used to identify a particular service chain within a network. So just keep this in your mind. The answer is 24. Nothing much here. So what is the purpose of match action table in P4? Okay, this solicits some level of explanation. Oh God. Okay. So we have, I mean, if you had seen the video, you must have seen something like this, right? And then something like this, right? Like this goes. So this is the match action pipeline, and and the pipeline basically contains match action tables. So these are match and action. So these are two separate words, right? You are matching something, and then you are taking an action based on that particular match. So first you match, and then you take an action, right? So let's assume a packet comes in like this, and this is basically a programmable parser. What does the parser do? Whatever packets come inside, it has a headers. It has all the headers. So this parser we are writing. So what it'll do is it'll extract all the headers. It'll strip out all the headers, and it will keep it in variables. I'm just explaining this to you in different terms. So we have it takes the headers out and it keeps it in local variables. In the P4 programmable switches memory, right? So these header fields, right? These header fields are then compared with the match action tables. So you compare it with the entries of the match action table, and then you apply a particular action. This action could be compare it with the next match action table, next match action table, next match action table, and finally you send it out after adding all the header fields. Right, so this is basically how a match action table looks. I'm just going to pass through this because it was already explained in the class. And if you have any specific questions, you can ask based on this. So you have these headers, and then you strip it out, and then you compare, and then you take some actions based on the matches, and then you send it forward. So now they're asking, what is the purpose of the match action table in P4? Right. So what is the purpose of the match action table? Is it to store packet headers and metadata? No, this is done by the PHP. So this is false. Right? Is it to perform packet modifications? No, this is not why match action tables are used, right? This is also false. Is it to perform lookups on packet fields? Yes. So lookups. So what is a lookup? It's like you take the packet and then you look it up on the match action table. So lookup means it's like you compare. That's what a lookup means. So this is what is correct here. So the answer is C. And or to perform packet forwarding. No, that's also not. I mean, in fact, you do end up doing packet forwarding after the lookup, but the purpose is not directly to forward packets, but to decide what action to take. So this falls in the context of it. So although packet forwarding happens after these match action table lookups, right? So the answer is C. So which of the abstractions does P4 support? So does P4 support protocol independence, compiler independence, target independence, or processing chain independence? So this processing chain independence means nothing, so eliminate it. So now we have three options. So although P4 is designed to be protocol independent in its operation, the question basically asks um, specific abstraction, which is basically here, which is not protocol independent. So for the context of this question, the answer is B, which is compiler independence. So that is before it kind of provides an abstraction that allows developers to write programs without needing to manage specific compiler details. So basically, I'm writing up code in P4. It is supposed to be cross-compiled to multiple targets. You don't have to worry about what kind of a chip that particular switch is using. It can be cross-compiled. It means that the same P4 code can be compiled by different compiler backends for various targets, right? So, and see, target independence, P4 does strive for some level of target abstraction, but it appears that compiler independence is one of the abstractions that P4 supports. So yes, at least at this point. So let's go with this B. This is the official answer. Okay. And then I think these are all repeated questions. Okay, it's not repeated basically. Okay, cool. So which of the following features distinguishes RMT from MMT and SMT? Right. So RMT is reconfigurable match action table. So this is one of those. This is basically one of those things that's similar to PISA, protocol independent switch architecture. So what this, so which are the following features distinguish RMT from MMT and SMT? So if we see the videos, it will be clear that the answer to this question is C. So basically it supports pipeline processing at different match action table. So it is basically distinguished by its support for a pipeline of processing across different match action tables. So the pipeline structure basically enables a more flexible and granular packet processing. So this is what RMT brings to the fray, which is called reconfigurable match action table. This is clearly explained in the video. In fact, there's a whole video for RMTs, right? So the answer is C. Next is, what does P4 stand for? So P4 stands for programming protocol independent packet processors. So answer is B. This is just the explanations. P4. So it contains 4 P's. First P, second P, third P, fourth P, right? So P4. What is the key difference between a traditional switch and a P4 programmable switch? So, I mean, what is the difference? Normal fixed function switch and a P4 programmable switch. The difference is basically, does it have a fixed data plane functionality in P4? Nope. P4 does not support hardware switches. Nope. Traditional switches have a programmable data plane. Nope. It's the other way around, right? This is pretty straightforward. That's why I'm just going through the options. So P4 defines data plane functionality. Yes, that's what P4 does, right? That's what happens in a P4 programmable switch. The other options are all converses of what it's supposed to be. So according to P4 design goals, right, what does protocol independence mean So as per P4's design goals, protocol independence basically means that the switch should not be tied to specific packet formats. In the sense, like OpenFlow, which only supported 40 header fields, if I'm introducing a new protocol which will contain different types of header fields, then OpenFlow fails. So here I am able to define the header field that the parser is supposed to look for. So in that sense, P4 is protocol independent, but it's a design goal of P4 and it actually works out similarly as well. Which of the following statements about programmable networks are not correct? So I think this is a repeated question and are not correct. So the answer is A and D. We did this question just before, I think it's just a differently phrased answer for that. So what is different here? Which of the following statements about the programmable network are not correct? Network that is pre-configured and cannot be changed. No, it can be changed. Programmable networks enable network administrators to program the behavior of network devices using software. Yes, this is true. And network that can be controlled and managed through software. This is also true. Programmable networks can only be managed in a based single centralized software controller. So this is false. So it is A and D. And this is a repeated question. What is the primary purpose of P4 network programming interface? So what is the primary purpose? It is to program the what? The data plane. Again, this is also a repeated question. Which of these is not a primitive action? Then I think yeah, it's basically C, and it is forward. Which of the following statements is not correct about P4 runtime? Protocol version 3. Yeah, these are all repeated. How many do these have? It is C, 24. And what is the purpose of match action table in P4? It is to perform lookups on packet fields, right? These are all repeated questions. So which of the following features distinguish RMT from MMT? So this support, sorry, the support for pipeline processing at different match action tables, right? So these are the kind of questions that you can expect from for this set of in this particular set of topics. And if you have any questions on any of these, you can ask me right now. I'll be here for another 10 to 15 minutes, right? If you don't have any questions, you're free to leave.
All right, then. So I'll end the session. Thank you for attending.